So good afternoon, everybody. My name is Tony Pope-Cruz. I am a Principal Solutions Engineer with Dynatrace. And in my time at Dynatrace over the last 13 and a half years, I've really been focused on helping our customer base with their monitoring and observability strategy, particularly nowadays as it relates to Kubernetes and other cloud-native technologies. So today I want to start off by beginning with a sad story. And unfortunately, this story does not have a happy ending. So this story is about a large retailer that lost a significant amount of revenue when they had an application outage. So this particular outage was centered around Kubernetes and the black hole of the inner workings of the orchestration engine. Specifically, it was related to the network and traffic routing of transactions in a large-scale, multiple application shared environment. So today we're going to learn a bit more about service mesh. We're going to take a look at the various features of the service mesh, including request timeouts, rate limits, and circuit breakers. And we'll explore the critical need for observability when running in these complex, high-load systems. So going back to our story, once upon a time, we have a large retailer, well-known e-commerce brand that will remain nameless for this presentation, that experienced a payment outage. So this particular retailer offered a special payment method for their loyal users, offered them the ability to pay via an invoice. So before offering users this payment method, of course, there had to be a risk assessment that was completed to determine whether or not that particular user qualified for this special payment method. Now, when this outage occurred, this actually meant that the payment option was completely lost and users were unable to submit orders, unable to make payments through their e-commerce platform. So what caused this? Well, that invoice payment method actually relied on a risk assessment service, and that service was served through the Kubernetes Ingress controller. And during the incident, they observed that there were many HTTP 5XX errors, and in particular, there were HTTP 502 bad gateway errors, which are really related to proxy and the traffic handling being unresponsive or unavailable. And if we look at that in more detail, the risk service is behind that Ingress controller. And there's actually another application in this shared environment that is behind that same controller. And during this outage, the Ingress controller became unavailable. And it turns out it's because the controller was actually killed by an out-of-memory event by Kubernetes. So wait, why would Kubernetes kill our Ingress controller? How does it run out of memory? So a quick refresher on how we manage CPU and memory resources in Kubernetes. We do this through the proper use of requests and limits. So when we start off with requests, pod containers are going to be scheduled based on the availability of CPU and memory resources. And if the container requests a certain amount of CPU or memory, and that those resources are available on one of the cluster nodes, and that pod can go ahead and be scheduled. Well, if the cluster, if the request definition of the request is too low, then the workload might not have the resources that it needs to be able to operate efficiently. And then conversely, if that request setting is too high, then you're really wasting those cluster-wide resources, potentially starving other containers from those resources as well. Then we have our limits. And with limits, these are the boundaries in which the CPU and memory can be used by the different containers on the cluster. And if the CPU limit is too low, then that container will be throttled. That's going to slow down your workload. Conversely, if the CPU limit is too high, then again, you are starving other pods of that time to be able to use the CPU resource. But from a memory perspective, if the memory limit is too low, then the container is going to be killed. So that is to say that if the container's memory usage reaches that defined limit, then Kubernetes will kill it and that container will be restarted. Okay, so how does an ingress controller consume more memory, ultimately hit that limit, and get killed? Well, in this retailer's example, it's actually because of the other application that was also behind that same ingress controller. So with the increase in load, the ingress began to queue those requests. As those requests queue, right, more and more threads are being utilized, more resources, and eventually the memory limit is hit. That container is then killed, and that stops all traffic from being able to come into either of those microservices, right? So, question is, how do we avoid this from happening? Well, what options do we have for exposing applications outside of the Kubernetes cluster? Well, the first method is using the load balancer type service. This is the easy way, the standard way of exposing a service. Very simple to do, especially with with the help of the cloud. But the downfall here is that it's going to create a public address for each of our load balancer services. So this means that you have additional cloud infrastructure, additional public IP addresses that you end up having to pay for. So instead, we can use a service mesh. And the service mesh will properly route and manage the traffic to those various applications that are behind the ingress controller. All right, blah, 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 more Kubernetes terminology and components. So what? How does using the service mesh actually prevent this type of outage? Well, let's take a look at some of the key features here of a service mesh. So when services are slow, we know that those can then impact other components on that same cluster, again, shared resources. So we can define a timeout to limit the impact to those upstream components. Then we can protect our services by applying a rate limit so that we don't get too many requests going into those microservices. So this will really help us to mitigate issues that arise from unexpected load increases. And then we can also block traffic from reaching specific pods that have been deemed unhealthy, overloaded, with the use of a circuit breaker. So starting off with the request timeout. So when we implement the service mesh and we define in our spec a timeout threshold, that will make it so that any requests that are taking that amount of time and reaching that timeout value will be automatically killed, and then an error will be returned to the upstream client. So remember in our retailer's example with their outage, requests were starting to slow down. That caused the queue, increased memory usage, and it killed our ingress controller. Well, with this configuration, those slow, unhealthy requests would be terminated and prevent the queuing that caused that outage to occur with our risk service. So essentially what this is doing is this is protecting that risk service from the other service when that other service becomes unhealthy. So of course, the owners of our other application service, they should still work on improving the reliability and scalability of their application. Next, we have our rate limit. So simply put, this allows us to use the envoy filter, for example, so that we can have a certain number of connections to that particular downstream service that's served up by the different pods, and then block any traffic to those containers that are above that particular rate limit during that time frame. Right. Then finally, the circuit breaker. So with the circuit breaker, this allows us to limit the traffic that goes to certain pods that make up a service that have been deemed to be unhealthy. So once that pod is healthy again and it's able to handle those requests, it's no longer overloaded, then the service mesh will automatically start to reroute traffic to that particular pod. So circuit breaker and rate limit are very similar and can generally be used together. So rate limit is also great for security use cases, such as mitigating DDoS attacks, right? And the requests that come in below the rate limit will be successfully proxied to that particular container and reach their destination. Meanwhile, requests above that rate limit are going to be blocked. So circuit breaker is really making sure that our load balancer doesn't oversaturate the pods by having those requests go to a pod, a container that is already overwhelmed and is only going to compound the issue that's occurring. right? So how else can we use the service mesh to really help us manage our microservices architecture? So some of the other features, some of the things that we can do that really complement the microservices architecture are things like retry logic. So being able to have it occur when a request fails from one service to another, that we can automate the retry of those requests to get an additional attempt or many additional attempts. And then, of course, authentication. So needing to manage repeated access across different services. Our certificate management of client and server on the different services that are part of our architecture. Getting observability into the inner workings of our inter-service communication and being able to understand if there are any problems that are occurring within that traffic. And then the traffic split allows us to manage our traffic, where it gets routed, how it gets routed, the distribution of requests against those different endpoints, and then, of course, managing security within your architecture as well. All right. So this is accomplished by the service mesh being able to automate these capabilities for us. So this is all done through the use of a sidecar proxy container. So as we deploy our pods as part of our microservices architecture, the application controller, application container will be running inside of that pod. And then the service mesh, the control plane, will deploy the sidecar proxy that has those configured capabilities that we're looking for. All right. So the configuration of the service mesh itself is performed through the control plane. So typically this is done through the use of an operator, and then we can control which namespaces in our cluster are utilizing that particular service mesh and how they're utilizing it. Then if we want further configuration of those specific capabilities, those are going to be deployed through CRDs using Kubernetes manifests that are applied to that target namespace that we are trying to control with the service mesh. So as those proxy containers are deployed into the pods via the control plane, all those rule sets that are there to help us manage our microservices architecture can be applied in real time. Now, observability. So how do we know what the service mesh is doing, whether or not it's healthy, and how the microservices that are being utilized are actually behaving? Well, thankfully, typically a service mesh will actually provide the observability signals that we need, such as our metrics, our traces, and our logs, to be able to understand the inner workings of the mesh activity. So health of the service mesh itself in the control plane is usually observed through the use of provided Prometheus metrics. And then the service mesh activity as it relates to the actual applications is observed through the metrics, traces, and logs that are produced by the service mesh sidecar container proxies. So we simply need to configure this to have these observability signals sent to our observability platform, such as Dynatrace, so that we can analyze, alert, and automate off of these different signals. So for the technical environment that we'll take a look at here today, we have a single Kubernetes cluster. We have 4 namespaces. Our application is deployed in the namespace Hipster Shop, and then we are using the Istio service mesh, and that control plane will be deployed in its own namespace. Then we have Dynatrace for observability, and then we also have the OpenTelemetry collector deployed in the default namespace, and all of our observability signals will be sent to the Dynatrace cloud. All right. So first thing, if we look at our Ingress gateway, we know that all requests that are going into our application microservices from outside the cluster are going to be routed through the service mesh Ingress. So here what we want to be able to do is track things like the throughput, the response time, and the failure rate of all these transactions, and this is going to be provided by the distributed tracing within the service mesh. Now, Prometheus metrics are available for throughput, response time, as well as failures. And these are going to be available at the workload level because these are provided by the sidecar containers. So as we have multiple deployments within our application, we'll be able to see how the traffic, the transactions are executing, how long are they taking, are there any issues with those at a per workload and per service level. And then in Dynatrace, these metrics will automatically appear alongside the telemetry that's captured for the workloads and the microservices themselves. All right. Next, if we wanted to look at the distributed traces and the spans that are being generated by the sidecar proxies, this is what allows us to really follow the transactions end to end, all the way from the entry point into the cluster through the Ingress, and then following that back through the microservices architecture. And I'm going to zoom in here. So in this example, we can actually see how the traffic first hits the transaction through the distributed trace. We see the first span is our hop through the Ingress gateway. The Ingress gateway then needs to route that to our front end microservice. And so in order to do that, that needs to go through the Ingress service within our service mesh. Now, of course, this front-end service that we're running depends on one or many microservices behind it. And so as those transactions need to flow through our architecture, those will go through the egress and ingress of their respective service. So here we can actually see how the front end making a call downstream to the product catalog service actually contains that egress call out of that particular sidecar container, and then going into the product catalog service, ingress service of the mesh before finally reaching the actual microservice itself. So the distributed traces, the spans that are generated by the service mesh allow us to really inspect what is happening and how those transactions are being routed and how much time is being taken at each of those different hops. And then, of course, in addition to timing details, the traces and spans are going to have an abundance of rich metadata that tells us more information about that transaction, such as the protocols that are being used, things like the HTTP response codes, any error messages or context attributes that are there on the span. And that's only going to further enable us to get better analysis of our telemetry data. Okay. And then by enabling the Envoy access logs, we can then see the details of each of those requests within our logs. And with Dynatrace, we can actually query these logs very quickly without having to set up or manage or build any indexes. And since we know that there's a certain pattern to the content in the logs, we can then parse that pattern so that we can dynamically create those relevant fields during our analysis. Now, going back to the three key features of the service mesh that we wanted to take a look at today. First, starting with the request timeout, what observability data do we get from that? If we look at our traces here, we can actually see that any time that our call to the product catalog service takes 2 seconds, right, that will be terminated by the sidecar proxy. And then we see that there's actually the error message that is there for us to be able to easily observe this. And then we can then take that information, we can chart that so that we can see how frequently this is occurring. And then of course we can set up alert notifications when this becomes problematic behavior. Now, when we apply the rate limit, any request to the service above that allotted throughput amount will be terminated. So here we can observe this again in the trace where we see the actual error details are captured. And then we want to make sure that we're graphing and trending these metrics that allow us to observe the number of transactions that were successfully made it through, as well as the overflow requests that were terminated because they were above the limit. And then when we apply the circuit breaker configuration, so we're doing this via a traffic policy. So when the product catalog service becomes overloaded and cannot handle any more requests, then that's where the service mesh is now going to terminate those requests. And then we see that in the trace data with the error message that is captured. But then the service mesh also provides a nice Prometheus metric for us to be able to graph this out and alert on it so that we can act on this information as it occurs. And then finally, when we want to deploy new releases of our microservices, we may want to use a canary release strategy to do so. This allows us to really limit the number of requests that hit that new version. This allows us to test and validate that there is this performance improvement and that we're not impacting all users and all transactions with this new code. So in this example where we are doing an 80-20 traffic split, we can actually observe where a transaction makes 3 calls to the product catalog service, where 2 of them hit the original version with a 1-second response time, while the 3rd call to that service has a much faster response time of mere milliseconds. Now, once we've validated the new release and the performance improvement, then we can simply modify our traffic to redirect all traffic to the new version. And our observability data here, after we send all the traffic, we can confirm the much improved response time as well as an 8x improvement in throughput. So what are the key takeaways from all of this? Well, first, managing resources in Kubernetes is extremely important, especially when you're dealing with large-scale implementations with many apps and many workloads sharing those resources on that cluster. So by defining quotas, requests, and limits properly, you can really mitigate the impact of heavy workloads and heavy resource consumption on other containers that are running in that environment. And then the service mesh allows us to utilize key microservice architecture capabilities in an automated fashion. This really alleviates your application developers from having to code these things into the microservices themselves. And then you need to know how the service mesh is behaving, both from a control plane perspective, as well as the requests going through your microservices architecture. And so the mesh provides the observability signals necessary to do so. However, signals on their own are completely useless. So you need a powerful observability backend, such as Dynatrace, that's actually going to be able to enrich, correlate, and analyze that observability data for you with the help of artificial intelligence. So if you're looking for more educational content on observability, Kubernetes and other cloud-native technologies, encourage you to check out our YouTube channel, Is It Observable? So this is hosted by my colleague Henrik, who's also the original author of the content that I went through today, where he has a multitude of informative videos to help cover these different topics. And then I'll leave this up here for just a moment so that you can copy if you want to look at the actual workshop that's out there on GitHub, so that you can actually deploy this onto your Kubernetes environment and see the observability in line with the Istio service mesh. All right. And with that, I want to thank everybody for their attendance and enjoy the rest of the conference. Thank you.